When an AI agent calls a write tool twice, should your system create two records, charge twice, or recover gracefully? In this lesson, we'll design MCP mutations that survive retries, reduce side effects, and stay safe in production. So far, we've built a path from MCP basics to secure access to reliable tool interfaces. You learned the mental model and production foundations, then added threat modeling, auth, scopes, tenant isolation, secrets, and auditability. Now we turn to safe mutations. Write operations that stay correct when agents repeat calls, retries happen, or partial success creates ambiguity. Reads are usually forgiving. A read tool can be called 5 times and nothing changes. A mutation tool is different. If an agent retries or infrastructure redelivers a request, one unclear action can become duplicate tickets, repeated payments, or deleted data. Safe mutation contracts make those repeats predictable. Before designing a tool interface, classify the tool by what it can change. Read tools only retrieve information, so they usually need lighter controls and simpler testing. Write tools create or update records, so they need clearer schemas, authorization, validation, and audit trails. Destructive tools delete, cancel, refund, revoke, or permanently alter important state, so treat them as high-risk operations with stricter permissions, confirmations, logging, and failure testing. The key principle is consistency. The risk category should be visible in the name, metadata, documentation, and operational controls. The useful mental model is proportional friction. A read tool, like searching documents, mostly needs access control, tenant isolation, and careful handling of sensitive fields. A write tool changes state, so it needs stronger guarantees: validation, authorization, idempotency, audit logs, and clear success or failure semantics. Destructive tools sit at the highest risk level because mistakes may be hard or impossible to undo. When choosing controls, ask 2 questions. How much business impact could this tool create, and how reversible is the outcome? A mutation contract is the safety boundary around any tool that changes state. It should answer 3 questions before execution begins. What are we trying to change? When is that change allowed? And what must be true afterward? Preconditions cover ownership, tenant scope, approvals, versions, and current status. Postconditions cover the new resource state, events, audit records, and structured output. Then define operational behavior. Can callers retry safely? Is the request idempotent? Can it be reversed? Does it run async? And what happens on failure? This turns a write into a predictable, testable commitment. Idempotency is the safety net for retries. When a client sends the same operation again, the goal is not to pretend the request never happened twice. The goal is to make every repeat converge on one logical result. The first call performs the work and records an idempotency key with the outcome. Later retries use that key to return the stored result, not create another charge, call another service, or change state again. For MCP tools, same intent should mean same outcome. Think of an idempotency key as the name of a user's intended operation, not just one HTTP call. When a tool request arrives, the server stores that key with the tenant, user, tool, payload hash, status, result, and expiration. If the client retries with the same key and the same payload, the server can safely replay the stored result instead of running the mutation again. If the payload is different, that is a conflict. For longer work, return an operation identifier so the client can track progress without resubmitting the action. A timeout is where many systems fail. If the client stops waiting, that does not prove the server stopped working. The mutation may still commit. If the client retries blindly, you can create a second order, send a second email, or charge twice. The fix is to record the operation, keyed by an idempotency key, before risky side effects run. Then a retry is not a new command. It is a status lookup or result replay. Good APIs make that explicit with states like completed, in progress, failed, rejected, or unknown, so clients can recover safely. Duplicate prevention is not one mechanism. Match the pattern to the kind of mutation. If the duplicate is a natural business conflict, like a second active subscription, enforce it with a unique constraint. If the same request may be retried, Store an idempotency record and replay the original result. If users can update the same record concurrently, use compare and set or version checks so stale data cannot win. And when a database change must trigger email, webhooks, or jobs, use an outbox or queue, so the side effect is delivered reliably without being fired twice. Before an MCP tool changes real state, give the agent a safe checkpoint. Preview answers. What would change? It should return the diff, affected resources, cost impact, warnings, and any permissions needed. A dry run goes one step further. It exercises validation and policy checks, but does not write anything. Only after the user or agent confirms should the commit call execute the mutation, ideally tied to a preview token or operation ID. Use this pattern whenever actions are destructive, expensive, broad in scope, or subject to compliance review. A useful preview is more than a friendly confirmation message. It should be a structured contract. Start with a plain summary of the intended changes, the resources affected, and the final state the system expects. Then expose anything that could change the decision: policy violations, required scopes, costs, irreversible effects, or warnings. If the user approves, the client should commit using a stable preview ID or draft operation token. That token must expire, and it should be invalidated when state changes. So approval never relies on stale assumptions. A safe commit is not just a button click. It is a second contract check. The request should be tied to the preview ID, idempotency key, actor, tenant, scope, and original request hash. Before executing, recheck authorization, policy, resource version, and business rules, because the world may have changed since preview. For risky operations, add stronger proof, like confirmation text, elevated access, or human approval. Then execute the transaction atomically and return a durable result or operation status. So retries are safe and outcomes are auditable. Safe mutations need evidence, not hope. Every request should leave a trace: operation ID, idempotency key, actor, tenant, tool, parameter hash, decision, and resulting resource IDs. Metrics should make risk visible, including replayed duplicates, idempotency conflicts, expired previews, commit failures, and destructive action volume. Before production, test the ugly cases: timeouts, duplicate delivery, partial commits, queue redelivery, and uncertain external APIs. Finally, audit records must tell the full story: who asked, what they previewed, what changed, and which policies allowed or denied the action. The core pattern is simple: classify the risk of every mutation, then apply controls that match the impact. Make retries safe with idempotency keys, operation IDs, and stored results. For high-risk changes, separate preview or dry run from commit. Next, we'll build on this with errors, retries, rate limits, back pressure, large results, and testing.